Okay. So today I have to sign you guys in for the, well, I was supposed to do it yesterday, but I'll get it done today. For the NAQ, the national qualifier thing. How many of you think you'll be participating? All of you here? Okay. Do you know any more people?
Yes.
So
Bemba,
here we have.
Yeah, Bemba, Paulina as well, Daniela. So that's at least 3 more that I can guarantee.
Okay, so for the qualifier, I'm just going to make random teams. Probably doesn't matter at this point. What I want to suggest for you guys. Oh yeah, by the way, whoever is watching, if you want to compete in the qualifier, which is day after tomorrow, right? I do have the timing information somewhere. Let's see.
It will be in teams, Professor?
So apparently we do have to register teams, but what I'm going to recommend for you is that you guys work from home or wherever it is you're working from, and essentially compete by yourself. I mean, if you solve problems together, they'll count the problems, but keep track of what you're solving so that I can figure out what your interests are and how to form the teams for later. Okay. That's all that I would recommend. But for now, I'm just going to make random teams. That's okay with you guys?
One thing is, I guess me and Nashville already registered.
Okay.
I got accepted.
For a team?
Just ourselves as our own team.
Bemba got accepted as well.
Okay. But were you put into a team already?
It was just us, yeah.
You just got registered, right?
Yeah.
Your information and then you got accepted through that.
There's a button that says that you compete as a coach, like you're a contestant coach. Yeah, and you put a team name and then you register and that's it. There's no one, you put a team name, but you don't put anyone in the team.
Uh-huh. And that makes you.
Yeah, that was allowed apparently. So I think that means only us were part of that team.
Uh-huh. Okay. So that also is okay with me. So can you send a message to everybody, to whoever you think might be interested, and we can get as many people competing as possible.
But the registration already closed, right?
Oh, it already closed?
Right, because it's not the 19th.
That is true. That did close, but they gave me permission to register you guys if needed today.
Oh, okay, perfect. See ya. Also, there's someone in chat. They don't need a petition for this, correct?
No, this is not this is just an open qualifier. Yeah. Yeah, I haven't responded about the petition, but I'll try and do that as soon as possible. Yeah. Okay, so that's about the qualifier. Right. So today we're going to do some combinatorics. And yeah, so there are a bunch of things that we will try and understand today. And then we'll have to find some problems for Saturday for you guys to go and try. But then this Saturday you're going to be busy with the qualifier. So not much that we can do. So let's see what we can learn today. Questions? Yeah.
This Saturday is the qualifier, but the problems for the ICPC, do they start as well? Or am I getting confused for next week?
Yeah, you mean the other
Saturday, Sunday.
Right. So that did say it starts on 22nd. So I'm not really sure. Those things are independent actually. So there is a no. That 22 is the year. Sorry. Yeah, it is 29. So it starts a week from Saturday. Okay. Yeah. So essentially, we have competitions, or at least mock competitions, every week from now until end of February, right? Okay. So let's start with the combinatorics. Anyone heard of Bob Dylan? Yes. This is his famous song. He even got the Nobel Prize, yeah, which he declined politely, not so politely. Sorry. Well, for I think for literature, yeah, for the poetry he's written. So some of the poetry is his own. So why am I putting this? Because it has the phrase "how many," and so we're going to be counting. We're going to be doing a lot of counting problems related to how many ways. So let me start with the first problem. This says how many ways can a team of K students be formed from a class of N students? You should remember this from your discrete math class, and the answer is N choose K, right? So N choose K, well, you don't need to remember the formula, but it's N factorial divided by K factorial N minus K factorial, right? Okay, so that was easy. This is just from your basics, right? Let me ask you a tricky question. What if the students are indistinguishable?
The order doesn't really matter, no? So
That's
it's
right.
just the combination.
Which is, what's the answer? They're indistinguishable. You can't tell the difference.
Wait, is N factorial?
Oh, no, it's N.
Sorry? Look, think about this. You all look at it, or just think that you have a basket of balls, and they all look identical. You're asking how many different ways can I pick up K balls out of the N basket of N balls?
Okay, N factorial divided K factorial times N minus K factorial.
That's the formula for N choose K.
They're all the same.
Is it just K?
They're all the same. That's right. The answer is 1.
Oh. Right.
I told you it's a trick question,
Yes, it is.
right? So there's only one way you can choose K people. You just take the first K. It doesn't matter. They all look the same, right? Okay, so let's ask a slightly harder question. You have this many girls and this many boys, and you want to team with that many girls and that many boys.
That's the answer, okay.
Now they're distinguishable. We're back to the distinguishable case. So forget the trick question. So what's the answer here?
Is it capital G choose lowercase g times capital G choose lowercase g?
That's right. Yeah. So pretty straightforward, right? Good. So we're comfortable with these basic counting questions. Let's make things a little more interesting. How many ways can we line up N students in a class? So if you have N students, how many different ways can you line them up? They're distinguishable now.
Is this the N factorial one?
This is the N factorial one, right? Because this is just permutations, right? So that part is easy. And if you only have K of the N students, then how many different ways can you line up K of N students?
So divide N factorial by N minus K factorial.
Think about this stepwise.
Right.
So your first job is to choose K. And how many ways can I do that? It's up there. And choose K. And then I have to line them up. How many ways can I line up the ones that I've chosen? K factorial, right? So it's going to be K factorial times N choose K, right? Okay, good. How many ways can N students sit at a round table? So instead of sitting on a line, you now have them sitting on a round table. So it's, the answer is?
The same thing but minus 1.
What do you mean? Is it n factorial minus 1?
No, isn't it n choose k?
There's no k here, it's just n.
Yeah. N factorial minus 1 because the last
N factorial minus 1. Anyone else? What's the logic? How did you get that?
because since it's like the one position where it's connecting right there,
Right?
it'd be equivalent on both sides. So I think you just subtract 1 because it's, I don't know how to.
Wait, is it minus 1 or minus n?
I don't know what to say, but
Look, an easier way to think about this is take one of the persons and have them sit in one place. Okay. Then you take the other n minus 1 people and you try every possible permutation of those. Is that clear? Now it becomes a linear permutation. Does that make sense? The reason there is a problem here is because why is that a problem? Why is it different from just counting on a straight line? Because the circle completes itself. The last one is next to the first one. And so what? What things are we counting more than once? Why is there a problem? Let's try with 3, right? Let's see if we can figure this out. So I have a round table. I have 3 people. Or maybe let's try 4 just to make things more interesting. So I could do 1, 2, 3, 4. I could do, so then let me not keep drawing the round tables. Let me just write down 1, 2, 3, 4. 1, 2, 4, 3. Is that a different order? Then what about 1, 3, 2, 4? 1, 3, 4, 2. Are these all different? Yeah? Okay, what else? 1, 4, 2, 3, and 1, 4, 3, 2. Are we good? And then I'm done with all, right?
Yeah, you're done with 1. Now you start with 2, right?
So then I have 2, yeah. So then I have 2. So now we're essentially writing all permutations.
Yeah.
And there are going to be quite a few of those. So that's, hey. So where does this run into a problem? Which ones are the same?
I believe since the problem is linear, like we do 1, 2, 3, 4, is that
It's the same as 2, 3, 4, 1, right? So 2, 3, 4, 1, whenever we get to it, is going to be the same as this. So we shouldn't be counting them twice. That's the problem. So obviously, you are you don't need that. So that means one way to get around this problem is to always put 1 at the first position, or only count the ones where 1 is in the first position, because then you won't have this problem. Does that make sense? So what's the answer?
N minus 1 factorial.
That's right, right? Because you're fixing 1, and then everything else can be whatever order you want. Okay, so that's n minus 1 factorial. Okay? So just watch out for these things. If these are clear in your head, then you can handle most of the simple counting things. Now let's get things a little bit harder. Well, some of these, yeah. So let's do this. Given n students, how many ways can we form a team with at most m people? this is kind of easy because it's very related to what we did here, right? Here we saw how many ways we can get a team of k people, right?
Would it be n choose m plus m choose m minus 1 and then all the way to
Right.
1?
So we're going to write this as a summation of n choose k, where k goes from all the way from 0 to m. Right? Yeah, here it's at most, so that's what it's going to be. If it's at least m, then you would go from m to n. Right? Okay. Here we could ask the question, what if the students are indistinguishable? Is that easy?
Oh, it's an m?
Yeah, would it just be M?
That's right. Yeah?
Okay. I thought it was another tricky one.
Yeah. All right, let's raise up the stakes a little more. We have n people, and we want to partition them into teams where the first team has n1 people, second one has n2, and so on and so forth. So we're making many teams now.
Or making m many teams?
We have m teams, yeah.
Wait, I'm sorry, you said that the subscript represents how many people are in that team?
Right. So the first team will have this many, second team this many, and the mth team will have this many. So again, it helps to think in steps, right?
Yeah.
So how many ways can you make the first team? It's going to be n choose n1, right? And then the second team?
And choose 2.
N choose n2, is that what you're saying?
No, and choose 2.
Well, remember, it's not 2, it's n1 and n2 and so on. So n1 may be 5, n2 may be 7, n3 may be 1, and so on, right? So what's it going to be?
We have to subtract from n the amount of players we have taken in the other
Right,
team.
right.
So now let's say we're at n3, right? That means that the other teams have 3 players, so now it'll be n minus 3.
That's right, yeah. So that means it's to pick up the first team, I have this many ways of doing it, right? Then to pick up the next team, I know that I've picked up that many already, so I have to take them out. And then over here, I'm going to have what? Right? Right. So it keeps going now. And at the end, you should have only nm left, and that's going to be 1. Yeah. So this formula, there is actually a cleaner way to write this, and it's typically written in this form. It's n choose n1, n2, and up to nm. And that's a standard notation for doing a partition. Okay? Here, we're assuming that these numbers add up to n. Okay? Are we fine with this? So this here is the same as this, it's just written in a different form. Okay with it? Okay. Yeah, we could ask what if they are indistinguishable. Is that easy?
Would it just be n minus n1, n minus n2?
You're going to add them up or multiply them? You want me to remind you what the answer was before when you only had to make one team?
So I guess add them up.
What was it when you had to make only one team? if you had to do k, yeah, it was just 1, right? So what's it going to be now? Sorry? nm. Why is it even nm? So, sorry?
1.
It's just 1. Why is it 1?
Because they're all multiplied times 1.
Right. So there's only one way I can make up the teams, because I can't tell the difference anymore. Even if I move some people around, as long as they have the same number, I can't tell the difference between this answer and another answer, right? So if I'm counting the number of ways, it's just going to be 1. Yeah?
If we do n minus n1, choose 1, that gives us 1?
N minus, no, that's,
Or will it give you n?
yeah, that gives you, n choose 1 is, if your question is what is n choose 1, that's n factorial divided by n minus 1 factorial times 1 factorial, which is 1, which turns out to be n.
Yes, okay.
Okay? So n choose 0 is 1. How many ways can you pick 0 people from a team? There's one way to do it, and that's not to pick anybody. Or n choose n, which is also the same as n choose 0. There's only one way to pick all of them. Right? Well, is this clear, or are you still a little mystified with that? Not happy? David's not happy.
So all the workers are indistinguishable.
Look, think about it this way. I want to make 3 teams here.
Yeah.
The first team has 2 people, second team has 3 people, and the third team also has 2 people.
Yeah.
I say, okay, these 2 guys go in the first team, you 3 guys go in the second team, and you 2 guys go in the third team.
Yeah.
Now, is there a different way to do this? Well, sure, I could move you and swap you with our friend here, but I can't tell the difference because they'll still look alike.
Hold on, but what if both me and Joseph went to this team and now Lazarus by himself? Isn't that a different?
No, but then remember, I have to satisfy the numbers.
Okay. Oh, okay. Oh, so they have to be a set number.
Right.
In each. Okay, oh, I understand now.
Yeah.
There's
Okay.
only one at that point.
There's only one, right? Yeah. Yeah, it just takes some thinking about what it's going to look like with real people, and then it's easy. What is this now? Oh, yeah, given n people, and I can't tell the difference, how many ways can we partition them into teams? Here, I'm not telling you how big the teams are.
So, like what I was saying.
Yeah, there it becomes more complex. There you have to actually do the computation. This problem is actually a little bit harder. It's the partition number. Yeah.
If you have n workers and they're
Yeah.
all the same,
Yeah.
so at this point is the question asking how many sets of length 1 is there, then length 2 is there, then length 3 are there from this?
No, I have to partition all of them into teams. So I have 7 people here.
But
I have to make teams, but I haven't told you what the sizes of the teams are. I haven't told you how many teams there are. I don't care.
So it can go from, the size of the teams can go from 1 or 0 up to?
That's right.
Okay.
I could just form one team with all of you,
Yeah.
or I could form 2 teams with 4 and 3, or I could do 2 teams with 6 and 1, whatever I like.
Yeah.
Okay? So, and they're all indistinguishable. They're all identical. Right? So this is called the partition problem. And it turns out to be a little bit more tricky. And it's a well-known problem that people have looked at and they've solved. You could also add a condition that says, I want the largest team to have k people. These are all minor changes to the problem. But there is a uniform way of solving all of these, and we'll talk about that. There is no formula. It's not a formula that you can write down easily. If there is one, I don't know it. I don't necessarily remember it. You have to write down what's called as a recurrence relation in order to solve this. Okay, so you solve them either using recurrence relations, or you use them, or you solve them using something called the what is that called? Yeah, it's called the. It's not the master theorem. There's a. You can solve them using some polynomial method. So I'll show you that in a couple slides. It's called the generator method, I think. Yeah. At the same time, you could also modify the problem saying I want exactly m teams, or I could say instead of largest team, I could say the smallest team must have k teams and so on. Yeah.
For that problem, the same n was equal to 3.
Which one? This one.
Yeah.
Yeah.
The same n is equal to 3, right? The first guy is in a team of size 1, and then the other two in a team of size 2.
Right. So
That's
yeah.
the same as saying that the first two are in a team of size 2, and then the last one is a team of size 1.
Right.
So they're identical.
Yeah.
So is this problem asking for the combination of the subset?
So you just want at least one of the teams to have a different size from. So let me show you with n equals 3. That's a good example. I could do 1 plus 1 plus 1. So that's forming 3 teams, each with 1 each. Or I could do 1 plus 2, which by the way is the same as 2 plus 1.
Yeah.
Or I could do all 3 in one team and nothing else. That's it. These are your only possibilities. Okay?
So, and that's why we care about the combinations, because the order doesn't necessarily matter.
Right. So you don't care which person went into this team. You don't care which 2 went into this team, and so on, because they're identical.
Okay.
I could swap one of these 2 with this guy, but it wouldn't make any difference because it would look the same. Right? All I care about is the size of the team. With n equals 4, it may be a little more interesting. So, well, let's start with the biggest guy. So I could make one team with everybody. Or I could make one team with 3 persons, and second team will only have 1. Or I could have 2 plus 2 or 2 plus 1 plus 1. Right? And finally, 1 plus 1 plus 1 plus 1. Did I miss anything? No, that's it. Clear? So there are 5 ways of partitioning 4. There are 3 ways of partitioning 3. Okay? You want to try 5, or you're okay with this? Well, there is no pattern. 5 is not going to be something that you can guess. We should probably do it. Let's do it. So n equals 5. I could have one team with all 5 members. I could do 4 plus 1. I could do 3 plus 2, or 3 plus 1 plus 1. Right? Then I could do. So you can see that I am making the first number to be the size of the largest teams, and then the smaller teams, and so on. Then if I make the largest team to have 2, then I could do 2 plus 2 plus 1, or 2 plus 1 plus 1 plus 1. Right? Remember, 2 plus 3 is the same as 3 plus 2. There's no point in looking at it. Right? And finally, I have 1 plus 1 plus 1 plus 1. So the answer is 7. Well, it doesn't mean that they go up by 2 every time. With n equals 6, it's going to be much more interesting. Yeah.
So from this pattern, it looks like we know we can always get a team of size n.
Yeah.
And then starting from the right, going to the left, the first number that's greater than 1, break it down, and then have 1 more.
Yeah.
Okay.
Yeah. So, yeah, you write 5, and with 4, you add to it the number of different ways you can do 1. With 3 here, you take number of different ways you can do 2, and so on and so on. So you see the recurrence showing up, right? That's clear. Yeah, good. So yeah, the recurrence relation, if you were to write it down, would look somewhat similar to what you just argued. Okay, and then I'm just going to give you a couple of these questions, and you can go and play with them later. They are harder, but it's, you can use similar approaches in terms of writing either a recurrence relation or using these generator functions. I have n workers standing in a line. How many ways can we form teams for m tasks so that all members of a team are consecutive in the line? That means I have n people standing in a line, and I have to make m teams. All right? If I decide to, so I can't have these two guys in team 1 and also these two guys in team 1. That's not allowed. Everybody in team 1 should be standing next to each other. Okay? That's the only constraint. And the question is, how many ways can I do this? Well, it turns out this is basically the partition problem, right? Because if the first team requires 4 people, I'm going to take the first 4 guys. That's it. I don't have a choice, right? If the next team must have 2 people, I'm going to take the next 2 people on the line. I won't have a choice. Things of that sort, okay? So it becomes a partition problem. So it's possible that the problem may be written in some strange form. You just have to map the problem to whatever you know. So that's the partition problem. What about this guy here? This is actually a slightly different problem, but anyways, you can still look at it. It says you're visiting a country where they have dollar bills of the amount 9, 17, 31, and 1,000. And you're asked the question, how many ways are there to change a $1,000 bill? Strange, but yeah, all right. So you could, you could return lots of $31 bills and then hope that the whatever is remaining adds up to the remainder, et cetera, right? Again, it's possible to write down a recurrence and then try to figure out what happens to it. Okay? For now, I'm just going to leave it this way. I'm not going to try and solve this. But I just wanted to give you a flavor of some of the problems. They are partition problems. They'll show up in some strange looking way. And here are some examples of things that might show up. Okay? All right. So a lot of these problems have to do with integer partitions. With integer partitions, we're basically asking the question, how many ways can we write down a number n as the sum of a bunch of positive integers? We shall call this answer to be P of n. P of n is called the partition number. It's how many different ways I can partition n as a sum of many different positive integers. Okay, so remember 0 is not a allowed number, but there may be situations where you may want to allow that. Anyway, so there are going to be situations where it's not exactly looking like this, so you just have to watch out. So the question is, can we write down a formula for P of n, right? This is what we have to figure out P of n. And the question is, how do we do this? And it turns out that there is a method called the generating function method where, well, first of all, I told you you can write it down as a recurrence relation. And that method you guys are familiar with. We kind of talked about it here. You can try that, and that works fine. I'm going to tell you a little bit about a different method called the generating function method. And in the generating function method, I'm going to write down a polynomial. And does everyone know what a polynomial is? So a simple polynomial is 2x cubed plus 7x squared plus 23. This is a polynomial where The coefficient for x cubed is 2, right? The coefficient for x squared is 7. The coefficient for x is 0. And the coefficient for 1 is 23. This is a polynomial in x. Right? Now, it's kind of strange to think that somehow we are going to use polynomials to do counting. How many of you remember seeing any of this in discrete math? Don't remember? You may have. Did they cover it in class?
It was like binomial theorem, a little bit.
Little bit, yeah, maybe, yeah. Okay, so what we're going to do is we're going to try and write down the we're going to write down a polynomial that looks exactly like this. So it's p of 1 times, p of 0 plus p of 1 times x plus p of 2 times x squared plus so on and so forth times all the way up to infinity. Now, what is p of 0? What is p of 1? What is p of 2? P of 0 is how many ways you can partition 0. P of 1 is how many ways you can partition 1. P of 2 is how many ways you can partition 2, and so on and so forth. All right? So this is called a generating function. Essentially, it gives you a formula for these guys. And instead of writing down each of these values, I'm just going to write down the polynomial. Now, question is, how do I do this? Well, here's the sort of the trick. Consider the product of these polynomials. Here's a simple polynomial. I have 1 plus x squared plus x cubed. Yeah? Very simple polynomial where every coefficient is 1, right? Then I'm multiplying it with 1 plus x squared plus x fourth plus x sixth and so on. So these are all the even numbers. Then here I have 1 plus x cubed plus x sixth and so on. So these are multiples of 3. Only the multiples of 3 show up, then multiples of 4, then multiples of 5, and so on and so forth. There are an infinite number of these polynomials, and I'm going to multiply all of them. Okay? Now, when I multiply all of them, what do I get? I'm going to get another strange-looking polynomial. But interestingly enough, it turns out that this product is exactly that. How the heck did that happen? Well, all the ones here will multiply and you'll get 1. Right? So the first one is just going to be a 1. And remember, the constant is p of 0, which is how many different ways I can add up numbers to get 0. There's only one because you're essentially adding, you're not taking anything, right? Then the question is, let's look at the coefficient of the term x in the product. How can you get x? So there is no x in any of these terms, right? Only x is showing up here. So this x has got to be multiplied by 1 in each one of those. So therefore, the coefficient of x is going to be 1. Right? And we know that p of 1 is 1. How many different ways can I partition 1? Well, easy. So let's write down a few of these numbers here. Here is I, and here is p of I. When it's 0, it's going to be 1. When it's 1, it's going to be 1. When it's 2, it's going to be, well, there are only 2 ways of doing it, right? For 3, we know it's 3. For 4, we know it's 5. And for 5, we know it's 7, and so on. Now let's take a look here. What about the coefficient of x squared? X squared only shows up in this and this term and nothing else. So therefore, we're only going to take the 1 terms from each of those guys, right? And we're either going to take this x squared and this one, or we're going to take this x squared and this one. That's the only, that's the only possibility, right? And so we get 2, which is exactly the coefficient for 2. All right, let's do x cubed. X cubed, we have either this or this should be possible. Which is roughly the same as saying either we get x cubed from here and 1 from everything else, or we're going to get x squared from here and x from here and nothing else. There are no other possibilities, right?
We can take the x cubed from the first one and times the 1.
Oh, that's right. So there are 3 possibilities, right? And the answer is 3. So what you'll see is that you kind of need to imagine this a little bit. If there are terms here that add up to a certain power, right? Sorry, multiply to a certain power, then that gives you one way of partitioning the numbers. Okay? And so therefore, every coefficient you get, it must be contribution from one possible way of writing down the partition. Does that make sense? A little bit tricky, but yeah. So here we wrote down many different ways of partitioning numbers, right? For each one of those, there's going to be a unique term contribution you'll get from the product. So there's a one-to-one correspondence between getting a term from this product and its contribution to the final answer. When you multiply this, if I want to look at, say, x to the power k, so I have x to the power k, and there'll be a coefficient. How does that, what coefficient will that be? That comes from how many different ways I can get x to the power k by taking entities from here and multiplying them. So if this and that multiply to be x to the power k, that's going to contribute 1 to my coefficient. And each such way is going to add 1 more. So therefore, this is exactly the way of partitioning k into positive integers. Is this weird or what? Yeah. But it magically works. Okay? And so why is this even useful? And that's where some of the next magic comes. So are you okay with believing what I just said? That this product, this strange looking product, is exactly that. You believe that? So, yeah.
So for that coefficient x and then for the power k, the coefficient will be
If k equals 3, yes. No, if k equals 3, then this number is essentially going to tell me how many different ways I can partition 3, which in this case is 3. If this is 7, if k is 7, it's going to tell me how many different ways I can partition 7, because each of those will contribute 1, and I'll have that product.
And then that 7 also tells you how many x's you can multiply to get
Yeah.
x squared to the power 7.
Yeah. Okay. So it takes a little getting used to it. It took me a long time, so don't feel bad about it not sitting with you right already. But after a while, you'll see that this is quite magical. Okay. All right. Then what? So who cares if this strange-looking product is exactly what you want? By the way, this is called the generating function because the coefficient is the magic that you really want to write down a formula for. Okay? And we won't exactly write down a formula, but at least we'll write down a way of computing that formula. Yeah?
Just for clarification, that 1 represents the last one is 1?
Yeah?
The last, all the way to the right? More to the right?
Oh, that's just the equation number.
Oh,
Forget
okay,
that.
okay.
Sorry. Yeah, it shouldn't be there. Yeah, I copied it from somewhere where they call this equation 1. Okay. Other questions? All good? Okay. Okay, so now comes the next magic. Question is, how am I going to figure this out? Well, this is where some of the work of Euler shows up. Euler was a famous mathematician. You'd have to look it up, but my guess is he was 18th century or something like that. Swiss mathematician, did some amazing stuff. And he figured this out. Now, we had a product of different polynomials, but he's writing this down in a different way. What is this? Well, let's go back and look at what we had on the previous slide, and maybe it'll start to make sense.
Professor, that's not the formula for E, right?
Well, Euler may have been involved in E as well. I'm not sure. Yeah, I think he was involved in that constant.
The series notation of E, doesn't it look like something like that? Am I
No, it's a sum.
No.
Oh, it's a sum, yeah.
Yeah,
you're right,
no.
it's a
E
sum,
is a sum.
Yeah.
So, remember what we said was that summation of p of k times x to the power k over all possible values of k, 0 to infinity. We said it's the product of strange-looking polynomials. The first one has all the powers, right? The second one has every alternate one, x squared, x fourth, and so on, so all the powers of 2. Third one had all the powers of 3. Then we had 4, then we have 5, then we have 6, and so on and so forth, right? Now, let's focus on this guy here. What is that? 1 plus x squared all the way up to infinity. Right?
If x is less than 1,
Sorry?
if x is less than 1, that will be a finite.
Then we know how to add this up because it's a geometric series. But we want to do something else. Because x, the value of x is not interesting to us. X is just a dummy that dresses up the polynomial. We are focused on the coefficients where x has no role to play. So we're interested in this. What happens if I multiply this by 1 minus x? The 1 stays, right? What else? you get minus x squared by multiplying these guys, and you get plus x squared by multiplying those two guys.
Oh, okay, then the x squared
Cancels
by
out.
itself and the x cubed by itself.
So x cubed will cancel out. X to the fourth will cancel out. Everything cancels out. Uno, that's all is left. Amazing, huh? So therefore, this whole thing is 1 divided by 1 minus x.
Whoa. Oh, wow.
Right? Isn't that strange?
That is like real.
So we don't really care about x anymore. So that's how he gets that.
That's a manipulation.
So this here is 1 over 1 minus x. This is 1 over 1 minus x squared, and so on. Beautiful, huh? So that's his formula for for this strange partition number. And well, these are just nice looking formula. What do we do with this? Well, there are a bunch of things that you could do. Yeah. So this is a setup for doing interesting things. If my question is, how many ways can I write n as a sum of positive integers, then I sort of know how to write this down. But what if I change my question to how many ways can we write n as a sum of positive integers, but we don't want to use ones? Well, if we don't want to use ones, then this is the guy that contributes the ones. Right? If I throw this away, then whatever I end up with, that's going to give me all ways of partitioning n so that I don't use ones. So this is, I'm going to call this, say, p prime of I. P prime of I want to know how many ways I can partition I in such a way that I don't use ones. So therefore, your 0 or your 0, there's only one way to do it. If I only have 1, that's actually a 0 because I can't do it, right? I can't write down the partition without using a 1. If I want to do 2, there's only one way to do it, and that's to just use the number 2 because I cannot use 1. Right? If I do 3, what's the answer? How do I get 2? I can do 3 and 0, right? Well, but I can't do 2 and 1. So there's only going to be 1. How many ways to do 4? So I can put all 4 in one team, or I could do a 2 and 2. That's it, right? What about 5? I can do 5 and one team with all 5. I cannot do a team with 4. I can do a team with 3, but the other one will have to be a 2, and that's it, right? So there are only 2 ways to do it. Let's just go one more step. 6. I could do 6 and nothing. I cannot do 4. I cannot do 5 and 1, so I'd have to do 4 and 2. I could do 3 and 3, or I could do 2, 2, 2. Right? So those are my, looks like 4 is the answer, right? So here's a magical way to do it. All you do is skip one of the polynomials, because I don't want sets that contribute 1. Remember, we had 1 times 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x cubed, all the other things, right? We just skip the one with 1 over 1 minus x.
Never mind. I was going to ask, like, if this could solve the problem with the change, and just use the sets of 1973 and the other one, but that's a not solve the problem.
That's a slightly different problem, yeah. Yeah. Does that make sense? Yeah?
Someone in the live stream said you can multiply out the 1 minus x and see how it derives to 1.
He wants to see it
Yeah,
again, he or she? Yeah.
Yeah.
Sure. So when I multiply 1 minus x by this, all right, so I get 1 times 1, that's 1. Then 1 times minus x is minus x. Then x times 1 is going to be x. Then x times minus x is minus x squared. Then I get plus x squared minus x cubed plus x cubed, and so on and so on and so on. This is never going to stop. Every term will immediately get canceled out. And so the only thing that's left is 1. Are we okay with this? So this general technique is called the method of generating functions. And essentially, you turn the problem into something that involves polynomials, where it's the coefficients that you're interested in. And there are many other problems where you could do similar things. What is this here, right? N is a sum of, oh yeah, so here I want distinct positive integers. What's that? If I give you a number like 7, I want to write this as a sum of different things, but they all have to be distinct. So let's figure out how to write 7. 7 can be written down as 7. It could be 6 plus 1. It could be 5 plus 2, but not 5 plus 1 plus 1, because then it would be no good. 4 plus 3, or 4 plus 2 plus 1. What else? 3 plus won't work, because then I'd have 2 2s. So I can't. That's it. This won't work. I'd have to stop there. Right? So there are only 5 different ways of doing it. So it's a slightly different problem, different partition. And look at this. If I write this down where the polynomials are slightly different, then I could solve that problem. So the reason I was using 1 plus x squared plus x cubed plus x fourth was because I could use as many 1s as I want. Now I'm not allowing that. I'm allowing only one of those. So I am only doing 1 plus x times 1 plus x squared times 1 plus x cubed, and so on. And I'll look at the coefficients of x to the k, and I'm done. All right, so now we're saying, let's call this new formula as f of x. So it's f of k, x to the power k equals 0 to infinity. This is what we want, where f of k is that strange thing. It's the number of ways I can write down k as a sum of distinct positive integers, right? I'm saying it's not equal to this, because this will allow me multiple 1s and multiple 2s and so on, right? Instead, I'm just going to do 1 plus x times 1 plus x squared times 1 plus x cubed. Oh, no, there's no plus there, sorry. That's the product I'm interested in. and I will look at the coefficient of x to the k, and I would have the answer. If you don't understand it, please ask. There's no shame in this. It's not easy here. So if I want x to the 7, right? I don't have x to the 7 here. I don't have x to the 7 here. So let's write down a few more terms here, right? Right? I get x to the 7 by taking x to the 7 here and 1 everywhere else, right? Remember, this 1 is the equivalent of 1 times x to the power 0. 6 plus 1, I take this x, and I take this x, right? So that's your 6 plus 1. So remember, think of this as your team of size 1. Think of this as your team of size 2, 3, 4, 5, 6, 7. Same thing over here. Think of this as 1, 2, 3, and so on. Okay? So if I want 6 plus 1, I take that 6 and that 1, and I multiply them. X to the 6 times x, somewhere it'll get multiplied if I take 1 everywhere else. That'll give me x to the 7. Or I could do 5 plus 2. That's x to the 5 and x to the 2 and 1 everywhere else. Right? Or I could do 4 plus 2 plus 1. I take the 4 here, the 2 here, and the 1 here, multiply them 1 everywhere else. Cool? Are you seeing this? And each of those will contribute a 1, and then when you add them all up, you'll get the count that you needed. Okay? So by writing down a different generating function, you could do all sorts of strange countings. Okay?
So the method starts at that step where you're generating the function itself.
Yeah.
We saw the first example where it simplifies to something easier.
Right.
With the Euler formula.
Yeah.
What is the advantage of using this over like a recurrence relation? Just because it's systematic, or?
Right. So a great question. Give me 3 more minutes, and I will get to it. Yeah.
Just to make sure I understand it, since we don't have any x's that have a repeating or similar exponent
Right.
in these groups,
Right.
to get an x to the power of k, for example,
Yes.
we need to be adding up unique exponents because
Right.
there's no possible way of getting repeating.
Correct. Yeah.
Okay.
And there are no repeated exponents.
Yeah.
And that's why it works. Right? If let's say I say you could use up to two copies of something. They have to be distinct, but it's okay if you use 2 copies. So you could use 2 2s or 2 3s or 2 7s, but no more than that. How would you do it?
With each group now, for example, first
You take the first one to be 1 plus x squared.
Yeah.
This will be 1 plus x squared plus x fourth, and so on. So as simple as that.
So previously, since it goes up to infinity, that means we
You could use as many ones as we wanted. Exactly. Right? Are we cool? Okay. Check this out. How many ways can I write down n as a sum of distinct powers of 2? So I can write 6 as 2 squared plus 2 to the power 1, right? Yeah?
Would it be what you have there, but skip what's not a power of 2 at the bottom?
Yeah, which is exactly what this says. You're only going to go 1 plus x to the power 2 to the power j. So you would have 1 plus x squared. You'll only have 1 plus x fourth, 1 plus x eighth, and so on. Okay? Good? So just playing around with this, you will have a setup for the next step, which is interesting. Okay? So question you were asking is, how in the world am I going to use these strange looking functions to figure out what I really want, which is my partition number? So here we use some differential calculus. Wow, where did that come from? Okay, so here's how this goes. You first write down your generating function, and then, well, you can take log on both sides, and then you differentiate. Whatever. Okay, if that's what you tell me to do it, okay, I'll do it. So you do all that, and then you'll see that magically it gives you the answer that you want. How? So let's say we start with, here we are doing it for f of x, but we could easily have done it for p of x, right? P of k. So let's say f of x is the generating function we want. Actually, we should just do this for p of n and see what we get. It's been a while since I tried this, so. Okay, so what do we have? Let's call p of x is the polynomial in x. And this comes from doing the product of 1 plus x to the power j plus x to the power 2j plus x to the power 3j all the way for j equals 1 to infinity. This is what we have, right? If j is 1, you get 1 plus x squared plus x cubed. If j is 2, you get 1 plus x squared plus x fourth plus x sixth and so on, right? So this is our original partition formula. Are you okay with this? Stop me here if this is not clear. Okay. Now we do a log. So let's do a log of p of x. Because it's a product, when I do a log, what happens? It becomes a sum, right? So I'm going to get summation j equals 1 to infinity of log of this guy. Fine? Are you okay with this? Log of a product is the sum of the logs, right? Okay, great. But we know that this here can be written in simple form if I want it, because this is equal to 1 over 1 minus x, right? So therefore, I'm going to replace this by summation of log of 1 over 1 minus x. Do we know how to? So now we're going to differentiate both sides. Yeah.
Isn't the x plus b to the power of j?
Oh, yeah. Sorry. Yeah. Absolutely. Right? It is j. Yeah, it is j. Because you want it to cancel out. right? Yeah. Then log of this is, sorry, so now I'm going to differentiate both sides. So when I differentiate summation, when I differentiate it, it's simply going to be sum of the differentiations of each of the terms, right? So when I do that, on this side, well, it doesn't matter what my this side is. And then you differentiate, that's going to be f prime equals that times f. Oh, yeah, all right, fine. So when I differentiate both sides, I'm going to get, what is the differentiation of the left side? Anyone know? No? Okay. It's going to be p prime x divided by px. Why? Because log of x, if you differentiate it, you get 1 over x, right? Remember this? No?
Yeah.
D over dx of log of x is 1 over x. So if you're doing, if instead of x you have p of x, then you'll get 1 over p of x multiplied by the derivative of p of x. So that's the derivative of p of x divided by p of x. Yes?
I thought those were natural.
Sorry? It's all the same. Yeah. Yeah, think of this as natural log. It doesn't matter. Okay? Yeah, you're right. Technically, there will be some extra constants, but it'll be on both sides and it'll go away. Fine? So the left side is this. What's the right side? Right side is simply the summation of the derivative of each of these terms. Right? So I get this is equal to summation over all possible j of the derivative of that, which is 1 over that quantity. So that's going to give me 1 minus x to the power j, right? And then I need the derivative of derivative of 1 over 1 minus xj.
Is that a chain formula? 'Cause it's
That's going to be a, yeah, that's going to be some nasty looking thing, yeah. So 1 over x, the derivative of 1 over x is minus 1 over x squared, right? So I'm going to get minus 1 over 1 minus x to the j whole squared, right? Multiplied by the derivative of 1 minus x to the j, which is minus x to the power j minus 1 times j. Something like that. I think I got this right. I don't have the details here, but we'll take a look. This minus sign and this minus sign will cancel out, right? You guys have given up on me.
No, no.
No, you're with me?
Yeah.
Okay, good, good, good. So here we have 1 minus xj whole squared. So one of these will cancel out, right? What do I have here? Summation over all j of j times x to the j minus 1 divided by 1 minus x to the j. That's what I get. Okay. Then what? Insert power series expansions for f and f prime and 1 over 1 plus xj. Oh, okay. Yeah.
Which one is the denominator there? The one, the 2 of them, right?
Or the prime is derivative of.
Right. So this came about because I took the derivative of log of something. Log of something will give me 1 over that something. Then I have to take the derivative of whatever is inside. To do the inside, I get all of this. But to do the inside, I have to do first the 1 over thingy and then the denominator, right?
Because they were over 1 over something.
Right.
Then the 1 over gives
So yeah, I'm applying chain rule twice,
Yeah.
so to speak, right? Okay, so then I have to plug in some things. What exactly am I plugging in? It says insert the power series expansions for f and f prime and that. So it's asking me to write down p prime of x to be equal to p of x times that guy. Right. Now I'm beginning to doubt myself. Am I going to finish this? Let's see. What do I get? How do I plug in the power series? So P of x, the original thing was it's the product of all that, right? See you later. So that's P of x. What is P prime of x? If I were to directly do the differentiation over here. Since it's a product, I have to hold everything else and differentiate one of them, right? Oh, okay. So I'm going to get a summation because I have an infinite series and then I have to hold one and differentiate, hold all of them and differentiate one of them. So when I differentiate this, I get x to the j minus, j times x to the j minus 1, 2j x to the 2j minus 1, and so on and so forth, right? That's that guy, and the other terms have to remain the same. Yeah, so the other terms are going to be pi k not equal to j, 1 plus x to the k, x to the 2k, and so on. So this here, if I multiply this by x, will that help me? I can pull out the j. How do I do P of n now? Okay, I may have to finish this next time for you because I don't necessarily know. I don't know how to finish this. There's something missing here for me. I'd have to check my notes before I can tell you more, right? Because I'm still missing what's happening here. So when you do p prime of x divide by p of x, what do I get? When I do this divide by this, all those terms are, so something is going to happen there. So this here is basically p of x divided by that missing term. Sorry, the missing factor. So I'm going to write this here as p of x divided by one of those terms. 1 plus x to the j, x to the 2j. That's what I have. Right. So now, when I take px and bring it down here, I will get a summation of jx to the j minus 1, 2jx, 2j minus 1, and so on. That's the numerator. The denominator is 1 plus xj plus x2j, and so on. So now, let's say I multiply the numerator by, no, that won't help me. And I need to bring it back to that guy there, and I still haven't quite done that. Right, in fact, this is exactly what I have here. I'm missing something here. I don't think I can finish this now, but I'll clean it up and get it to you. Okay. But basically, it's playing around with some amazing algebra and some amazing differential calculus to figure out something that seems completely unconnected, and that's some counting numbers. Okay. So you will be able to write down some way of computing your partition numbers. Yeah.
So we have to go through this process for each of those previous formulas that solve different questions to get to the previous infinite answers.
Right. So this did give you a simple way of doing partitions, but the nice thing is, as I showed you there, it allows you to handle variance, and in a very uniform way. You can go through the same steps and figure out how to compute any of those partition things that you want. Okay. Now the question that I also don't have quite an answer for is, how is this different from the recurrence relation approach? And is that easier or is this easier? Those are things I'll try and tell you next time. Okay. But I hope that this was somehow, well, it's clearly not useful yet, but it will become useful soon. Okay?
Thank you, Professor.
All right.